Thank you very much. Good morning, everyone. First of all, I would like to thank the organizers for the invitation and the opportunity to give this talk. It's my great pleasure. During this talk, when I refer to a ring, I will mean a commutative ring with unit. Assume that we have an m times m skew-symmetric matrix. I mean a matrix of this form. The elements of the main diagonal are equal to 0, and each element which is below the main diagonal is equal to the opposite of the corresponding element up to the main diagonal. If n is even, then the determinant of this matrix is equal to a polynomial in a square. We call this polynomial Pfaffian of the matrix A, and we will denote it by this symbol. And at this point, you may say that I'm cheating, because there is also another condition that I will not refer to it, but it's a little bit technical, and I will avoid it. So if we have a 2 times 2 skew-symmetric matrix of this form, as a first step, we compute the determinant. We can see that it is equal to the element A12 in a square. So we call Pfaffian of this matrix the element A12 if we omit the square. If we are in the odd case, so n is odd, we call Pfaffian of A this set, where by AI we denote the skew-symmetric submatrix of A, which is obtained if we deleting the ith row and ith column of the matrix. So if we come back to the 5 times 5 matrix we saw before, and we want to specify the matrix A1, as a first step, we just delete the first row and first column, and we have this remaining matrix. If we compute the determinant of this matrix, we will see that it's equal to a polynomial in a square. This is the polynomial. So we call Pfaffian of A1 this polynomial if we omit the square. For the definition of Pfaffians of the other matrices, we work in the same way. Now I'm going to introduce an important class of rings, which appear often in many fields, such as ring theory, commutative algebra, and of course algebraic geometry. These are the Gorenstein rings. Here I will give a definition, but in fact there are many equivalent definitions for this notion. So we call that an Eulerian local ring R is a Gorenstein ring if it has finite injective dimension as an R module. Or more generally, we say that an Eulerian ring R is Gorenstein if for every maximal ideal of the ring, the localization of this ring with respect to this ideal is Gorenstein. There are many examples of Gorenstein rings, such as the canonical ring of a smooth Fano n-fold. In what follows in the talk, I will try to construct this type of rings. The canonical ring of a smooth regular surface of general type, and also from the combinatorial side of things, the Stanley-Riser ring of a simplicial sphere over any field. For Gorenstein rings of codimension less than or equal to 3, we have good structure theorems. More precisely, Searle proved that if the codimension of ideal is equal to 1 or 2, then the ring is Gorenstein, if and only if it's a complete intersection. And Bushbout and Eisenbach in 1977 showed that if the codimension of the ring is equal to 3, then our ring is Gorenstein, if and only if it's generated by the 2n times 2n Pfaffians of a skew-symmetric 2n plus 1 times 2n plus 1 matrix with entries in the polynomial ring. So at this point, we pose the following questions. What about Gorenstein rings of codimension greater than or equal to 4? Is there a good structure theorem? That is a theorem which describes the exact form of the ideal in this case. Kusten and Miller, trying to answer this question unsuccessfully, introduced a procedure which constructs more complicated Gorenstein rings from simpler ones by increasing codimension. This procedure is called Kusten-Miller projection. And some years later, Miles Reid rediscovered what was essentially the same procedure, working with examples of Gorenstein rings arising from K-free surfaces and threefolds. The assumptions that we set in order to perform Kusten-Miller projection are the following. We have a codimension 1 ideal, which lives in a Gorenstein ring, such that the quotient ring is Gorenstein. Under this assumption, Reid proves that there exists an extra map, phi, such that home is generated by the canonical inclusion and this map as an R module, and defines as the unprojection ring of this pair the graph of this phi. In this type of unprojection, in Kusten-Miller projection, the codimension is increasing by 1. Reid and Papadakis proved that the projection ring is Gorenstein. Some remarks related to this ring is that has typically more complicated structure than both the initial ring and the quotient ring, and is useful to construct and analyze Gorenstein rings in terms of simpler ones. Kusten-Miller projection is intended for serial use. This means that it can be used many times over an inductive way to produce Gorenstein rings of arbitrary codimensions, whose properties are nevertheless controlled by just a few equations as the numbers of new variables are adjoined. These new variables are called unprojection variables. It finds many applications in the construction of some new interesting algebraic surfaces and threefolds. This is how I use it. In the explicit birational geometry, in the sense that we can write down explicitly morphisms and rational maps that minimal model program says they exist. And also it found some applications in algebraic combinatorics. In 2013, Neves and Papadakis developed a theory which is called parallel Kusten-Miller projection. More precisely, they set sufficient conditions on a positively graded Gorenstein ring and a finite set of codimension 1 ideals, which ensure that we can perform a series of unprojections. Furthermore, they give a simple and explicit description of the end product ring, which corresponds to the projection of the ideals that we start. It is important to say at this point that this theory applies when all the projection ideals of a series of projections corresponds to ideals already present in the initial ring. What does it mean? It means that all the ideas that we want to unproject are appeared from the beginning. We don't meet new ideals during the process, new ideals loci, as we say. Okay, Before I introduce the Tom and Jerry triples format and explain what it is, let's meet the main players. Let's meet Tom and Jerry. Tom and Jerry are two families of unprojection which are originally defined and named by Miles Reid and are related to the construction of codimension 4 Gorenstein rings starting from codimension 3. But also let's see in which question these two families answer. Assume that we have a codimension 4 complete intersection idea, and then a 5 times 5 skew-symmetric matrix. What conditions can we set in the entries of the matrix M such that if we take the ideal of Pfaffians of this matrix be contained in the ideal J? Tom and Jerry families are two different answers to this question. So we call the matrix M Tom matrix in J if after we delete the ith row and ith column of M, the remaining entries are elements of the codimension 4 ideal J. Let's give an example. Assume that we fix this ideal, the ideal J, and let's observe a little bit the matrix N. We can see that this matrix is a Tom1 matrix in ideal J, because if we delete the first row and first column and check the remaining entries, which are general elements of this ideal, we see that the conditions for a Tom1 matrix are satisfied. So N is an example of a Tom1 matrix. In a similar way, the matrix M is called Jerry IJ if all the entries of M that belong to the ith row or ith column or jth row or jth column are elements of J. If we set these conditions in the entries of the M and after that compute the Pfaffian ideal, we will see that the Pfaffian ideal is contained in the ideal J. Let's return back to this Tom1 matrix. We denote by I the ideal generated by the Pfaffians of this matrix. And if we set the generators of this ideal, it's easy to conclude that is contained in the codimension 4 ideal, intersection ideal J. Papadakis, using this unprojection pair, computed the codimension 4 Gorenstein ring, which occurs for this, for the Tom family. In the following two slides, I will try to give a sketch of the main steps of his computation that we will use below, as we will see. More precisely, using multilinear and homological algebra, calculates the equations of the codimension 4 ring, which occurs as a projection of the pair. He calculates 4 specific polynomials, which we denoted by GI, and he defines the map phi in this way. And he proves that this map with the inclusion generates home as R over I module. Then, from the general theory, it follows that this ideal of the polynomial ring RT, where by T we denote the new variable, the projection variable, is Gorenstein of codimension 4. Okay, I think now that we are ready to define Tom and Jerry triples. But before I give the strict definition, I want to discuss a little bit in which question this format answers and why it's maybe useful. Assume now that we have three complete intersection ideals of codimension 4 that we denoted by G1 up to G3 and the 5 times 5 skew symmetric matrix. The question that we set is, what conditions should the entries of this matrix satisfy such that if we compute the ideal of Pfaffians of this matrix, this ideal to be contained simultaneously in the ideals G1 up to G3. Tom and Jerry triple sum projection format gives one answer in this question. We say that M is a Tom 1 plus Tom 2 plus Tom 3 matrix in ideal J1 up to J3 if it's Tom 1 in the first ideal, Tom 2 in the second ideal, and Tom 3 in the third ideal. I will give an example of this type of matrix immediately. Assume that we have these ideals, C1 up to C3, we fix them, and we consider this matrix. The claim is that this matrix is a Tom 1 plus Tom 2 plus Tom 3 matrix in this ideal. First, we should check that it's a Tom 1 matrix in the first ideal. So we delete the first row and the first column of the matrix, and if we check the remaining entries, we can see that are contained, this part of matrix, that are contained in ideal J1. This matrix is a Tom 2 matrix in ideal J2 because if we delete the second row and the second column and we check the remaining elements here and here, we can see that it's contained in ideal J2. In a similar way, doing the same procedure by deleting the third row and third column, we can check that it's also Tom 3 matrix in the third ideal. Are there any questions so far?
Not in the chat for now.
Okay, thanks. There are also some other formats, Jerry, 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 Tom, Tom, Jerry, and Tom, Jerry, Jerry, which are defined in a similar way, and I will not refer more on them. Let's return back this. We denote by I the ideal generated by the Pfaffians of this matrix. And in what follows, I will try to prove that this initial data, ideal I with J1 up to J3 ideals, satisfy the conditions which are set by Neves and Papadakis for parallel Custom-Miller projections. We have this initial data, and we prove that for all T with T between 1 and 3, these ideals are codimension 1, homogeneous ideals, and the quotient is Gorenstein. Moreover, for T and S distinct between these bounds, it holds that the codimension of the sum of ideals is equal to 3. These are the first conditions that are set for parallel Custom-Miller projection. As a second step, we should define three maps, three phi. We have one phi for every ideal. We have three ideals here, so we have three phi. In order to compute these phi's, we take into account that our matrix is a Tom 1 in the first ideal, and we recall that, for example, for the computation of the phi 1, phi 1 is related with ideal J1. Our matrix is a Tom 1 matrix in the first ideal. We recall that Papadakis' calculation is related to a Tom 1 matrix in his ideal. So for the definition of phi 1, we just repeat Papadakis' calculation. we make some obvious substitutions and we can easily define our phi1. For the definition of phi2, we are taking into account that our matrix is a Tom2 matrix in the second ideal. So, as a first step, we should convert the Tom2 matrix into a Tom1 matrix. And after that, we can just repeat again the Papadakis calculation. But we know that the Tom2 matrix is related with the Tom1 matrix using some elementary row and column operations. So we do this process and we work as the previous case for the definition of phi2. We work in a similar way for the definition of phi3. And we saw that each of these maps, phi1 up to phi3, together with the canonical inclusion, generates home as R over I module. It is not difficult to prove this because, as I explained previously, our phi's defined as a specialization of Papadakis phi's. Papadakis, in his computation, proved that his phi, together with the canonical inclusion, generates home as R over I module. So the same holds for our phi's. Moreover, for all T and S distinct, it holds this inclusion. And this proposition completes all the conditions that our initial data should satisfy in order to perform parallel custom-Milan projection. So, from the theorem, there exist homogeneous elements A and T that we can compute, such that this equality holds. And now we have on our hands all the main ingredients in order to write down the Fano definition as this definition is described in Papadakis and Neff's theorem. Neff's and Papadakis theorem. We denote by T1 up to T3 three new variables, then projection variables, and using the elements that we computed before, we write down the final ring, and we denote by Rn the quotient ring. It is important to say that this ideal, the final ideal, is a codimension 6 homogeneous ideal. It's easy to compute the codimension because we started by codimension 3 ideal. We performed 3 custom-Milan projection, and as we saw before, in each projection, the codimension is increasing by 1. So we have that the end product is of codimension 6. It has 20 generators. We can count. We have 5 generators from the Pfaffians and 15 new, so total 20. And this set of generators is a minimal generating set. In order to prove this, we use the ideal of specialization again. This means that I put sum of Ci to be equal to 0 and sum of Ci be equal to 1. And I check that the final ring after this substitution has some generators which are monomials and some others which are binomials. And it was really easy to see that it's a minimal generating set from the form of the final ideal. And also the final ring, this ring, is a Gorenstein ring. This is because our initial data, the I ideal and the J1 up to J3 satisfy the conditions of parallel custom-Milan projection. Then from the theorem, it is known that the final ring will be Gorenstein. Before I define the four intersection format, let's discuss about another question, which is related to the format. Assume that J is a fixed codimension 3 complete intersection ideal. The question that we set here is, what should be the form of this ideal in order to be contained in J? One answer of this question is given by the following calculation. We fix J to be this codimension 3 complete intersection ideal. We denote by A this matrix, and by AI the 2 times 2 submatrix of A, which is obtained by removing the ith column. We consider also the ideal I to be of this form, and it is not difficult to see by observing the generators that this ideal is contained in ideal J. For this initial data, ideal I in J, Papadakis computed the equations of the codimension 3 Gorenstein ring, which occurs from this unprojection pair. More precisely, denoted by HI, the polynomials which is equal to the determinant of the submatrix of I, he defines the map phi in this way. And he proved that home is generated as R over I module by the inclusion map and this phi. Then again, from the general theory, it follows that this ideal of the polynomial ring is Gorenstein of codimension 3. What about our format? What four intersection format does? Assume now that we have 4 codimension 3 complete intersection ideals. The question is, what conditions should satisfy the generators of a codimension 2 complete intersection ideal in order to this ideal be contained simultaneously in each of ideal J1 up to J4? Four intersection format gives one answer in this question. We say that I is a four intersection ideal with respect to the ideals J1 up to J4 if phi is a subset of each of the ideals J1 up to J4. An example of four intersection and projection format, which we use later again, is this. Assume that we have this polynomial ring. We set I1, 2, 3, 4 to be this ideal, and we can easily check that this ideal is a codimension 2 complete intersection in each of ideal J1 up to J4. Just checking the generators again. For this initial data, ideal I1, 2, 3, 4, and ideal G1 up to J4, I checked that we can perform parallel Kusten-Milan projection using similar approach with before. Let's discuss a little bit in this format how we can define phi. We observe that our ideal is again a complete intersection ideal in each of ideals J1 up to J4. And we recall that Papadakis' calculation is about, again, a complete intersection ideal inside a complete intersection ideal. So our phis are again defined as specialization of Papadakis' phi. We denote now by T1 up to T4 before new variables of degree 3, and we can write down the final ring. Now we have 4 new variables because we started by a codimension 2 ideal and we performed 4 unprojections. And using the same arguments as before, how this codimension changes during the projection, and counting the generators, we have that IN bar is a codimension 6 Gorenstein ideal with 20 generators. Okay. As I said before, all these formats had as motivation some applications in geometry. And more specific applications for the construction of some interesting families of Fano threefolds. And now you can ask me, okay, why are interesting? What is the special feature of these families? Why we want to construct them, to prove the existence? And I will reply that one of the major problems in algebraic geometry, and I think in geometry in general, is the classification of geometric objects. More minimal model program is devoted to the classification of some interesting geometric objects. Fano threefolds with a specific type of singularities, with singularities in the Moore category, are one of the building blocks of this program. So we are interested to know more and more about them. Moreover, these families are noted in graded ring database. Graded ring database is a database due to Professor Gavin Brown and his collaborators, which contains conjecturally the existence of some interesting geometric objects, such as Fano threefolds and others, which are again conjecturally are related to varieties of lower codimension via custom projection. What we are doing here is to use the two formats, Tom and Jerry triples and foreign intersection, and more precisely the rings that we constructed using these formats, in order to prove the existence of some families which are contained in this database. The first family is described in this theorem. It's a family of quasi-smooth, projectively normal, and projectively Gorenstein Fano threefolds, non-singular away from edge singularities of this type, quotient singularities of this type, with the Hilbert series of the canonical ring be equal to this quotient. I will sketch the proof for this family. The second family is again a family with the same general features, which belongs to this projective space with this type of singularities and Hilbert series to be equal to this quotient. About the construction of the first family, the family that is described in the first theorem that we discussed. We start by the ring that we constructed using Tom and Jerry triples and projection format, the Aran ring. And in order to prove the existence of this family, we're just playing with the degrees. What I mean? I mean that as a first step, we set C1 up to C25 with a general element of K25. And we set the other variables to be equal of degree 2. That is what I said before in the reply of the question, that we need space in order to have possibilities for good geometric constructions. This means that we need more and more variables in the polynomial ring in order to have good geometric objects as we want, from singularities and so on. So, using this putting these degrees on our variables, we have a an object which leads to the weighted projective space P to 10. So, putting the variables to be of these degrees, we constructed an object which lives in this weighted projective space. But according to the theorem, we want an object which lives in this projective space, weighted projective space. We don't have the right object. We need three more variables of degree 1, and we have three more variables of degree 2 that we don't need it. So we put three variables of degree 1, I'm sorry, we denoted by D1 up to W1 up to W3. We consider three new variables of degree 1. And the three more variables of degree 2 that we don't need, we just substitute with general elements of degree 2 in the other variables. This is what describes this map psi, that we replace Z4, Z6, Z7 with general elements of degree 2 in the other variables. And now we have the right object, the object which lives in the right weighted projective space. We have an object of codimension 6, as we said before. So the group dimension of this ring is 4. So the proj is 3-dimensional. We checked using Macaulay 2 that this is an integral domain. This quotient is an integral domain. And moreover, using Macaulay 2 and singular, that the only singularity of our object is on the vertex of the cone, and that the intersection of our object with this singular locus of the weighted projective space is exactly 8 points, which are quotient singularities of this type, as exactly described in the database. Moreover, we computed the graded resolution, and we saw that it's equal to this, and the canonical module, which is isomorphic to this. So the negative number here says that it's a Fano. Okay, about the Hilbert series is equal to this quotient. It's easy to compute because we can compute the Hilbert series of the initial object of the codimension 3 object, and we know how Hilbert series change during the projection. So we can compute that the final ring has this, the final object has this Hilbert series. Okay, and using the same ideas, the playing with degrees and so on, but now using the Aran bar from 4 intersectional projection format, we proved also the existence of this family. And now I will give 3 slides of references. This is the central paper about parallel customary projection that I referred many times before.
Is there another question? Seems that there was a raised hand for a moment, but I don't know.
Okay, let's give the last slide, and of course later we can discuss whatever you want.